Hello, my name is Abigail Aquino, and today I'll be presenting the paper PCC Vivis Online Learning Congestion Control by Dong and colleagues, published at the NSCI 2018 conference. This paper introduces Vivis, a congestion control algorithm that brings ideas from online learning and machine learning inspired optimization into the networking world. Vivis builds on the earlier PCC framework, performance-oriented congestion control, and addresses many long-standing problems found in traditional TCP congestion control, as well as newer algorithms like BBR and PCC Allegro. Today, I'm going to explain why we need new congestion control, what problems existing algorithms have, the design and contributions of Vivis, and finally, the experimental results that show how well Vivis works. Topic Introduction. Before going into Vivis, let's start with what congestion control actually is. Every time we stream videos, play online games, or download files, our devices must decide how fast to send packets across the internet. If the sending rate is too high, routers and network buffers get overwhelmed, causing queuing delays and packet loss. If the rate is too low, we waste bandwidth and get poor performance. The challenge is that modern networks are vastly more complex than they were decades ago. We now rely heavily on Wi-Fi, LTE, 5G, satellite networks, and multi-hop cloud infrastructures. These networks are highly variable, unpredictable, and often noisy. Traditional congestion control algorithms, especially TCP, fall short of ideal performances in these environments. So recent research has tried to improve congestion control by leveraging ideas from machine learning, specifically online optimization, where the system actively learns from performance rather than relying on static rules. Vivis follows this trend. It adopts PCC's high-level architecture, measures performance, evaluate utility, adapt rate, but it updates the entire framework using modern learning theory, making it far more stable, accurate, and efficient. Why new congestion control? So why do we need a new approach at all? TCP's congestion control, like Grenell and Cubic, was built decades ago for wired low-loss environments. Today, the design is outdated because TCP converges very slowly, so it takes a long time for multiple flows to share bandwidth fairly. It performs poorly under non-congestion laws such as Wi-Fi interference or random LTE drops. It suffers from buffer bloat, meaning it fills up queues and causes huge latency spikes. It can be unfair with some flows grabbing more bandwidth than others. These weaknesses cause many of the real-world problems we see today. Video buffering, inconsistent download speeds, lag in games, and unstable cloud connections. Vivis was created specifically to fix these issues and adapt smoothly across different environments. Existing alternatives and limitations. Before Vivis, several attempts were made to improve congestion control, but each had major flaws. REMI uses offline machine learning to guarantee congestion control rules, but since it relies on pre-known assumptions about network behavior, it becomes fragile when real-world conditions differ even slightly from its training. BBR from Google uses a white box model that estimates bottleneck bandwidth and RTT. While often fast and efficient, BBR can become unstable or overly aggressive when network conditions change unpredictably or when its model is inaccurate. PCC Allegro, Vivis' predecessor, is closer to the right idea. Instead of using lost signals or models, it directly measures performance and chooses rates accordingly. But Allegro still has big shortcomings. It uses an arbitrary utility function, it doesn't handle latency well, it converges slowly, it has high loss at equilibrium, and it can be too aggressive towards TCP flows. Vivis was designed to solve all these problems while keeping the strengths of the PCC approach. Vivis' key idea and contributions. The first major contribution of Vivis is its new utility function framework. A utility function is like a score that tells Vivis how well a given sending rate is performing. Vivis utility incorporates three key components: throughput, which it wants to maximize; loss, which it wants to minimize; latency, measured using the RTT gradient, not raw RTT. The RTT gradient, the change in RTT over time, is an important innovation. Instead of looking at the absolute round-trip time, Vivis focuses on whether RTT is increasing, which indicates queue buildup and potential congestion. This design is more accurate and avoids misleading signals that occurs in networks with naturally high RTT, such as satellite links. The author also shows that under certain parameters conditions, this utility function is concave, guaranteeing fair and stable equilibrium even when many senders compete. The second major contribution is Vivis online learning-based rate control. Vivis uses no-regret learning, which means that over time its performance approaches that of the best fixed rate it could have chosen, even without knowing the future. Here's how it works. Vivis runs monitor intervals, also known as MIS, where it tests performance at two nearby rates, slightly above and slightly below the current rate. It measures utility at both rates. It estimates a gradient based on which rate performed better. It adjusts the sending rate using gradient ascent. This is very similar to how machine learning algorithms optimize their loss functions. Compared to PCC Allegro, Vivis removes fixed step sizes, has a smarter, more stable update mechanization, reacts faster to changes, handles noises more efficiently. This makes Vivis both faster and more stable in practice. The third contribution is the experimental results, and they are quite impressive. Vivis was tested in many environments and consistently outperformed PCC Allegro, TCP, and BPR. Some of the headline improvements include 70% less packet loss, 72% higher output than Allegro, 20% throughput gain over BPR, 2 times faster convergence than Allegro, 2 times more stability than BPR, and 57% less video buffering time. These results highlight that Vivis isn't just theoretically better, it delivers meaningful improvements in real performance. Vivis online learning approach. Let's look deeper into how Vivis conducts its learning. Vivis operates in monitor intervals, MIS, to sample performance. It does short periods during which it sends traffic at a chosen rate. After each interval, it gathers performance data and evaluates the utility. A helpful analogy is walking. If you're trying to find the fastest pace you can walk without getting out of breath, you walk a bit faster to test it. And if it feels good, you continue. If not, you slow down. Vivis behaves in exactly the same way. It also addresses several problems found in Allegro. It filters out noisy RTT spikes so that momentary jitters don't mislead the algorithm. It double checks abnormal readings that doesn't make sense. It safely backs off if a monitor interval times out as well. This robust approach is essential for handling real-world networks, which are noisy and unpredictable. Utility function details. Vivis' use of the RTT gradient rather than absolute RTT is one of its greatest strengths. Absolute RTT can be misleading. A satellite network might have a higher baseline RTT even when it's not congested at all. By measuring the change in RTT over time, Vivis can detect congestion earlier and avoid buffer bloat. The concave utility design also means Vivis can converge cleanly without oscillating or crashing into unstable behaviors. Evaluation results. What Vivis improves. Number 1. Random loss resilience. In lossy environments like Wi-Fi and cellular networks, Vivis performs slightly better than traditional algorithms. The experiments show Vivis maintaining over 90 Mbps until 3% random loss and staying above 80 Mbps even at 3.5% loss. In contrast, TCP variance dropped drastically, even by 20 to 50 times more. This makes Vivis extremely robust in the modern wireless world. Number 2. Satellite links. Vivis also performs exceptionally well on high latency satellite links with 800 ms RTT. Despite the high delay, Vivis reaches over 90% of link capacity, outperforming BBR by 20 to 40%. This demonstrates that Vivis' learning-based approach handles long-delayed networks far more efficiently than traditional or model-based algorithms. Number 3. Buffer bloat and latency control. Buffer bloat is a real-world phenomenon where larger router buffers cause huge latency spikes. Vivis handles this gracefully. It avoids building large queues, it maintains low latency, and it keeps packet loss minimal. This comes from using RTT gradient as an early warning sign, allowing Vivis to react before buffers overflow. This also helps the lower packet loss compared to BBR and Allegro. Convergence speed and stability. Another key result is Vivis convergence behavior. Vivis converges twice as fast as Allegro and is more stable than both Allegro and BBR. BBR often overshoots or oscillates. Allegro is slower to adapt. Vivis strikes a strong balance between reactiveness and stability, which is extremely rare in congestion control. TCP friendliness. Any new congestion control algorithm must play nicely with existing TCP flows. Vivis is more TCP friendly than BBR Allegro. It avoids taking over bandwidth aggressively, which is essential for real-world deployment where many applications still rely on TCP. Another one is real-world internet test. The author tested Vivis over 42 Wi-Fi to AWS paths, representing a real everyday condition, and to real-world problems. Vivis latency achieved 11.6% better median throughput than BBR, 3.7 times better throughput than TCP cubic, and lower variance, meaning more stable, predictable performance. This is strong evidence that Vivis works well in real internet environments, not just controlled testbeds. Limitations and future work. Despite its strength, Vivis has a few limitations. Its specialized LTE conditions and algorithm called Sprout can outperform it. Integrating Vivis into systems like QUIC or Linux requires more engineering work as well. There are also opportunities for integrating Vivis with centralized SDN systems for even more controlled bandwidth allocation. Conclusion. To conclude, Vivis achieves substantial improvements across all core metrics: throughput, latency, fairness, convergence speed, stability, and TCP friendliness. Its use of online learning and gradient-based optimization marks a meaningful shift in how congestion control can be designed for the future internet. And because Vivid requires only sender-side changes, it has strong potential for real-world deployment. This is also the reference I use for this slide. Thank you for listening.